using the Nernst equation to calculate non-standard cell voltage. So the Nernst equation is giving you the value for each cell under any conditions, i.e. when we do not have standard conditions of temperature and commonly concentration. So we take the standard cell potential, which has that little degree symbol, and subtract from it minus RT, where R is the gas constant, T is the temperature, over N, the number of electrons transferred, times F, the Faraday constant, multiplied by the natural log of Q, which is the reaction quotient. So you guys remember that from doing equilibrium, etc., that the reaction quotient is non-equilibrium values substituted into the equilibrium constant expression. So what do we have to calculate? Well, real quick, we can just do temperature. So 25 degrees plus 273.15 gives me 298.15 Kelvin. Now I can sleep at night. Then N, we're going to have to work out. F is the Faraday constant and R is the gas constant. So R is 8.314 joules per mole per Kelvin. And the Faraday constant, F, is 96,585. Is it? Hang on. I'm sure there was a 4 in there. Coulombs per mole. This is the problem when you try and memorize constants. It's always an issue. Have to look it up. Yes, that is a 4. I knew it. 96485. My bad. I'm just going to cross that out. How can I make it look so ugly? 9, 6, and then 485. Stop trying to memorize constants. Okay, so there we are. 96485 comes from. Anyway, so then Q, we're going to need to write an equilibrium constant expression based on what we see here in our balanced redox equation. So Q is going to be the concentration of calcium 2 plus raised to the power of 3. Solids do not appear in a heterogeneous equilibrium, right? So anything to the concentration or partial pressure, and that will be divided by my chromium 3 plus, and that will be raised to the power of its stoichiometric coefficient, which will be 2. I've been given those concentrations, so I can go right ahead and calculate that number. So that is going to be 3.69 molarity, and that will be cubed divided by, oh no, not cubed, sorry, squared. My bad. 3 calcium. Calcium, there's too many like same letters. That will be cubed, I'm sorry. It's 3 moles of calcium, and then it's the chromium that there's 2 moles of, and that will be my 2.13 is my concentration of my chromium raised to the power of its stoichiometric coefficient, which will be 2. So that comes out to be 11 point something, 074. That's probably enough siggy figgies for now. All right. So we can just bank that. Okay, so we've got our value for Q, we've got our R, we've got our T, we've got our F. So the only thing we have to work out is our standard cell potential and our number of electrons that are being transferred. Okay, so let's work out what's being oxidized, what's being reduced. We've got +3 oxidation state, 0. And then we have the 0 for the chromium. And then calcium is going to +2. So we can see that chromium is being reduced from +3 to 0. So that is my reduction, and that is occurring at the cathode. And I can see that my calcium is being oxidized. So that will be the reaction that is happening at the anode. So then if I go ahead and get my ALEKS data tab and look up the standard reduction potentials for each of those half reactions, and of course half reactions are always written as reduction. So I'm going to have my chromium 3 plus, and of course stoichiometry is just going to be like a 1-to-1 stoichiometry when you look these things up. So chromium 3 plus 3 electrons gives me a chromium solid. If I look that up That's what I'm going to get. So my reduction potential for that is minus 0.744 volts. Okay. And then I'm going to look up my calcium couple. And again, that when I look for it, it's going to be a 1-to-1 stoichiometry and it's going to be written as a reduction. So it's going to be written the other way around, right? Calcium 2 plus AQ plus 2E minus gives calcium solid is how it's going to appear in my data tables, and I get minus 2.868 volts. So now we have to shake up what's actually occurring. So I'm glad I wrote that down already. So my chromium is going in the forwards direction as written, so it is being reduced. So this is my reduction, and that is occurring at the cathode. My calcium is going to actually run as an oxidation, and that is occurring at the anode. If it helps you to visualize, because I know we're going to have to add these together to work out n, the number of electrons being transferred, I would actually go ahead and rewrite this the way around that is actually occurring, and it should match your overall balanced equation. So you can see here that the electrons would actually be on the right hand side. So in order to get it to cancel out, I can see that I'm going to have to multiply by 2 integers but each line. Okay, so I'm going to have to multiply these guys by 2 altogether before we add, and multiply these by 3 in order to get those number of electrons to cancel. So I'm going to do a little sneaky cheeky copy and paste, and then this should match my overall equation, and the number of electrons that are cancelling out are going to be my number of electrons that are being transferred in the overall process. So I end up with 6 and 2 like so, and then I'm going to end up with 3, 3, 6 like this. So then when I add these two together, overall my 6 electrons are going to cancel out, right? So 2 chromium 3 plus AQ plus 3 Ca solid. It should match the equation we were given upstairs. CRS plus 3 calcium 2 plus AQ. So we can say confidently N equals 6. 6 electrons are being transferred. Okay, and then the other thing we have to do is actually work out the standard cell potential. So that is going to be the cell potential of the cathode minus the cell potential of the anode. So just as they have come straight out of your standard reduction potentials, right? So the cathode we identified was the chromium couple, so that's minus 0.744 volts. Then subtract from that our anode, so minus and minus gives me a plus, 2.868 volts. So that is going to give me my standard cell potential of 2.124 volts. So that's net positive standard cell potential, so that should be spontaneous as written, and that makes sense because the more negative out of those two standard reduction potentials is going to be the one that actually runs as the oxidation, which, as we can see from looking at the numbers, is the calcium half reaction. So that makes sense that that is the one that actually runs as the oxidation. So lastly, we can actually go ahead and calculate what our E cell is under the non-standard conditions, and I should be good here and give you this, right? Give you the little symbols. They're just a pain in the butt to put in, I'm going to be honest. Okay, so E cell then is going to be my standard cell potential, 2.124 volts, then minus RT, so R is 8.314 joules per mole per Kelvin, and then my temperature is in Kelvin, so 298.15 Kelvin, so we can see that's going to cancel out, divided by my number of moles of electrons, so that's 6 moles of electrons, times the Faraday constant, which is 96,485 coulombs per mole, and then times the natural log of Q, the reaction quotient, which we worked out to be 11.074. Make sure that you enter this in your calculator carefully, using parentheses where required, etc. So we are not sad that our calculators upset us. So you're probably going to have to do, quite a few brackets to make this work. I don't know exactly, depends on your calculator. So we're going to get a number out of this, and I got 2.11370 blah 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 volts. We've been asked to give to 3 significant figures, so 2.11. Okay, so a little word to the wise. Our standard cell potential under standard conditions was 2.12. Under non-standard conditions, it's 2.11. You will quite often find that this is the case, regardless of how much the concentration changes, that your actual cell potential under non-standard conditions is very similar to what it is under standard conditions, which is why batteries work and work and work until suddenly they don't, right? There's just a very sudden drop off in the current that they produce, sorry, in the voltage that they produce, which is when the concentration really suddenly drops off.